in the last lecture, we started with the basic hypothesis or basic rule of StatMech, which says that you take a macro state consistent with a certain energy, volume, N and M. There are many microstates associated with that macro state, many of them. And then you say, I give them all equal probability. So that is the rule number one. So if the number of microstates consistent with a given macrostate is omega, then the probability of a microstate is 1 by omega. And so given this microscopic calculation, you have to connect to thermodynamics, and that connection is given by saying entropy is k log omega. Okay, so only these two rules are required to do all calculations. So then we did some examples. One was the ideal gas in d dimensions. We got back the ideal gas equation of state. Then we were doing some model problems to just make this calculation more and more imprinted in your head. So one was you take a lattice and put these particles non-interacting. Then we made them indistinguishable. The equation of state changed. Then we introduced some interaction, hardcore interaction. The equation of state even changed further. Then I gave you two problems to do, which is you have V sites, N indistinguishable particles. There's hardcore interaction, but now with the constraint that at most two particles can be on one side. And the other problem was there can be at most two particles on one side, but if there are two particles on the same side, then the system has energy epsilon. Okay, and then once the question is posed, the calculation is the same. You have to compute omega of E. So was it able to compute? Was anyone able to compute this? Okay, so something we see. Okay, I think that seems all right. Okay, so let me do that on the board. So a certain there are V sites. One microscopic configuration might look like this. And this is energy minus 2 epsilon. Right? So if I want to ask what's the energy of a microscopic configuration, I just have to ask how many pairs are there on one side. So let us say, so now we want to compute omega of k, comma v, comma n, where k is a number of such, where energy is equal to k times epsilon. So there are k such pairs. So now how will I distribute these? So I want to distribute n particles such that on k sides there are 2 of them and the remaining are randomly distributed. So the first question is choose k sides. How many ways can I do this? In VCK ways. Once I choose these k sides, I have only one way of putting 2 particles there. How many particles remain? Remaining particles is n minus 2k and v minus k sides. In these sides, they can be maximum 1 or 0. So how many ways can I do this one? So remaining number of ways is v minus k c n minus 2k. Okay. So therefore omega omega becomes VCK, V factorial by K factorial. That is this one. And then this, which is and V minus N. So this is the answer that you have found. Then these two cancel out, and you're left with V factorial by K factorial, N minus 2K factorial, V minus N. K. But remember, your K is what? N plus K factorial, but before that, your K is E by epsilon. So I'll just replace wherever K comes with E by epsilon. E by epsilon factorial. Now we are back to our what we want to do. We just take log omega. So S becomes log omega, which is roughly, I'm putting K equal to 1. This is V log V. All the minus V's will cancel because these all add up. N minus 2K minus K is N minus K. When I add to this is V. So I just have to keep V log V minus E by epsilon log E by epsilon minus epsilon minus V minus N plus E by. Maybe okay, so see earlier when we were doing the random walk calculation, we were taking N factorial is N to the power N plus half E to the power minus N root of 2 pi. Now when I'm writing log N factorial, I'm writing it as N log N. Why is that? These other terms are important. There's a minus N, but because the numerator and the denominator add to the same value, these arguments, they'll all cancel out. Root of 2 pi is just a number. While we are dealing with numbers of very large numbers, the root of 2 pi don't matter, and half is small compared to N. So that is the point. When you take logarithm and you divide by N in the end, those half doesn't matter. So that is okay. So now we have, unlike before, we have energy also coming into play here. So I want to, so let us as an exercise find out the equation of state for this problem also. So remember your dE was TdS minus PdV plus mu dN. This is from thermodynamics. So if I do del S by del E, I should get 1 by T. And if I do at constant volume and N, and if I do del S by del V, I should get P by T. So we have to just use these two equations. So let me just differentiate once, because the curve looks quite nice in the end. So it is worth doing. Is everyone following this calculation? Okay. So 1 by T, I'm going to differentiate with respect to, okay, P by T first. I have to differentiate this with respect to volume. First term gives you 1 plus log V. Then I go here, I go here, I go here, this one. The first term gives you minus 1. And then I get minus log V minus N Z by epsilon, right? V by epsilon, which is equal to log V by E minus N. So this, since E and epsilon, E by epsilon comes all the time as that, I can just call it back to K. Okay, E by epsilon. I divide by V, I get log minus log 1 minus rho plus small e by epsilon, where small e is the energy per particle, per volume. That is. Okay, now what about now I take my second derivative here. So I get 1 by T. When I differentiate with respect to E, first I get minus 1 by epsilon minus 1 by. That's when I differentiate this one. Then I differentiate this, I get minus plus 2 by epsilon log N minus 2 E by epsilon. Then I differentiate the logarithm. That 1 by thing cancels with this. So I get minus 1 into 2 by epsilon with a minus 1. So plus 2 by epsilon. Okay. And finally I have this one to differentiate. So I get minus 1 by epsilon log V minus N plus V by epsilon minus 1 by epsilon. Okay, if I have done correctly, that is the answer. So immediately all these constants go away, the non-logarithms go away, and you're left with 1 by epsilon times log, so I'll take this epsilon by T is equal to log N minus 2E square by this one by E by epsilon and V minus N. And then I can take my V common outside, which is log rho minus 2E by epsilon by E by epsilon. Okay, so we have got two expressions: pressure in terms of density and energy in terms of epsilon by T, temperature in terms of energy and density. Okay. What we want is the equation of state. Equation of state, when we tell for ideal gas, we have pressure is equal to rho T, right? And so we don't want energy to come there. We want to eliminate energy. So I have two equations and I want to eliminate E from there. So I can look at this equation, find out the expression for E, substitute back here, and I get my pressure. Now I don't want to do this algebra. So what we will do is, let me first check whether I got the answer right. Epsilon by T, something like this. P by T is minus log 1 minus rho plus E, and epsilon by T is is rho minus 2 epsilon the whole square by E into 1 minus 1 plus C minus rho. Okay. So what we will do is we want to make a plot of pressure versus temperature. So what I will do is I will do this on because we don't want to make algebraic errors and we also want to plot. I'll do this on Mathematica. Does everyone know? You don't have to know Mathematica, but how many of you have used Mathematica before? Some of you have used. But anyway, the expressions are quite the new document. And let us make it 125%. So we are going to solve for E. If I type something, can you see? Too small. Okay. So 300%. GF. That's visible? 250%. 300%. 8G. Okay. So for we look at the first equation. So this I can just solve by hand. This implies e to the power minus p by t is 1 minus rho. E by epsilon I will define as E tilde plus E tilde. Okay. And here I am going to write this as just to make the log of rho minus 2 E tilde the whole squared by E by E tilde, and 1 minus rho plus epsilon is e to the power minus p by t. E tilde into e to the power p minus t, right? And epsilon by t, I'll keep as epsilon by t. What do I want to find? Yeah. I want to, in this expression, I'm going to put e tilde to be e to the power minus p by t plus rho minus 1. Okay. So let me solve the equation. So exponential of x epsilon. I'm typing in this equation. Epsilon by t minus right hand side is rho minus 2e, escape rho minus 2 times e. E is your e tilde, but I cannot put e tilde here. Oops. Rho minus 2e by e tilde is e into exponential minus p by t. So exponential minus p t. I have typed right here. I have taken the e to the power this, and I am subtracting out rho minus 2 epsilon the whole. We want to solve this equation, right? Rho minus 2e by e exponential. This is not energy, so this I call energy, En. E has a different meaning, so En. But we know what En is, so I'm going to put En is equal to e to the power minus p by t. That is from here. E is e to minus p by t plus rho minus 1 plus exponential rho minus 1. Agreed? So I found out my energy. I'm looking at the other expression here, and what I want to find is pressure as a function of rho and temperature. Okay. So since e to the power p minus p by t comes, I'll call that as x. So I will remove this and put x here, and I will put x here. Huh? So I want to solve this equation equal to 0 for x, and I'm solve. Okay, and it's a quadratic equation, and you have solved. So x is e to the power minus p by t. Remember, x is, so just to note it, x is e to the power minus p by t. So we have now solved for pressure, but there are two roots, so we have to be careful what to choose. So if I choose the first one, so let us choose the first one. I will C, S1 equals, and S2. Let's call them as two solutions, S1 and S2. Only one of them can be right. But to determine which is right, if one of them is negative, but x is here e to the power minus p by t, which is positive. If one of them happens to be negative, we can throw that away. Okay, so we have got some expression for this. So let us choose some value. Temperature T equals 1, epsilon also equal to 1, let us say, and plot S1 for rho from 0 to 1. And that is negative. So S1 is the wrong answer. If I put S2, I get the right answer. It is positive. So we'll choose the one of the roots which is positive and clear. Is it clear what I'm just finding out, trying to solve for pressure as a function of density and temperature, which I have done now. So from x, so if I take log x, so log x is minus p by t, so pressure is minus t log x. So we have to just plot minus t log x, and what we will do is, wherever temperature comes, temperature always comes as epsilon by t, because these are the two energy scales, they have to always come in that ratio. So what we can do when you analyze is put temperature to 1 and then vary epsilon. Okay, so temperature equal to 1, so this is minus log x. So now we are going to plot pressure is minus log x, so minus log x. Okay, so what we want to plot is plot of minus log of, and our x was S2. S2, let's keep rho, comma, for densities, density can go from 0 to 2. That's the maximum density. We cannot do that because temperature and these are not fixed. So we fix temperature to be T equals 1. Let's keep epsilon equals 0, 1. And the pressure looks like this. At 2, it should diverge, because that's the maximum density possible. Is it clear? First thing to check is, see, we have done this calculation where when I put indistinguishable but non-interacting, I got log 1 plus rho as the answer. When I did indistinguishable but hardcore interaction, I got minus log 1 minus rho as the answer. If I put epsilon equal to 0, I get the at most 2 Ks. If I ignore energy completely, I get the at most 2 Ks. So let us plot when epsilon equal to 0, pressure as a function of this one. And along with that, let us plot minus log 1 minus rho minus log S2 and log 1 plus. And now you can see how the 3 curves have changed. This was the, oops. This was the hardcore interaction. This was the boson type indistinguishable, no restriction, and this is the one restriction 2. Okay, so you are able to solve that problem also in this case. So now let us make epsilon higher and higher. So I am going to make energy, the energy when two things come together, more and more repulsive. So if I make epsilon equal to 10, and I want to remove, let us not worry about this one. Let us forget about these things now. Now you see there's a nice kink in the pressure. So, oops, sorry. This is pressure, this is density. Maximum density is 2, it becomes infinity here. But it does not like two particles to be on top because it is very repelling. So when the density goes from 1 to higher, then immediately things start pairing, and you can see the density has a sharp rise there. Okay, so on the other hand, if I had made density 100, I cannot plot maybe, but let me make 50. It even becomes is not able to plot. Okay, so it is having a very sharp increase. Okay, so, and it's not able to plot very well because the numbers become too large. On the other hand, if I make the interaction attractive by making epsilon negative, so let's make it -1, and this can be. It is and along. It is a nice smooth function. Even the other ones are smooth functions only, -2. It doesn't seem to affect so much because there is no difficulty in putting particles on top of each other. So when I go from repulsive to attractive, the nature of pressure changes quite drastically, and it's a nice solvable problem in which even with energy you can solve. Okay, now we will keep this Mathematica file open because we have to check something later. Then, and I want to clear. Okay, we'll keep it here because I want to do this calculation one more time to show how. Is this calculation clear? Okay. Now, you saw that it becomes more and more difficult to count for omega. If I had put at most 3 particles per side, you would have struggled even more. So, not easy to count omega, that is one point. Also, that system was defined, that set of rules were defined for systems which are isolated. Energy is not, is a fixed, energy is fixed, N is fixed, V is fixed. But most systems are not like that. Most systems are not isolated. So, for example, if I take something, this particular light, it is in thermal equilibrium with the air outside. So, temperature is fixed, but energy is not fixed. Okay, which is so most of the time things are interacting with this environment, and you would like to know, in such a case, how do I assign a probability to each microstate? So, let me give this example. Now, N is fixed, V is fixed, but temperature is fixed now, but energy we can exchange. So, energy is no longer a constant. Once we discuss this example, you can do any example you wish, starting from the microcanonical ensemble. You can derive rules for any such problem. So, in this case, there are many microstates consistent with given T, N, and V, and you would like to assign a probability to each of these microstates. Previously, when energy was constant, we could assign equal probability, but now energy is not. Each microstate comes with different energy, so they may not have the same probability. So, I will do a quick derivation of the answer. So, the derivation comes from rule number 1. Okay, and Yeah. So the equivalent derivation. So you take a large system in which is microcanonical, which is isolated. So it has a total energy E total, N is fixed, V is fixed. In this system, you take a particular, what is the word for that? A subsystem here, E, actually this N and V, anyway, N and E subsystem here is a hand waving derivation, let us say. A subsystem here, E, which can exchange energy with the reservoir. So the remaining part I'll call as reservoir, and this subsystem I'll call as the system of interest. Now, I want to know if I have a particular microstate with energy E, what is its probability? And now, but we know for a particular isolated system how to compute the probability. The probability of the microstate is proportional to the remaining energy is distributed in the reservoir. So omega reservoir of E total minus E. Okay. And E total is much larger than E. So when I exponentiate, I get e to the power s times E total minus E. I do a Taylor expansion. This is fine, and I get a derivative of del s by del E, which I know is 1 by T. So I get e to the power minus E by K. So that is a quick derivation of what is the probability that a certain microstate has energy E is e to the power minus 1 by Kt is often called beta minus beta times E. Okay. But we can state this as rule number 2 rather than, even though we can derive this, we will define this as rule number 2. If temperature, volume and N are kept fixed, that I'll call as canonical ensemble, the other one was microcanonical ensemble, and we just derived that the probability of a configuration of energy E is proportional to e to the power minus beta E. So we have again assigned a probability for a system which is not isolated. And then if I want to make it a probability, I have to normalize it by summing over all the configurations with energy E. This denominator is often called the partition function. All these things I am just repeating, most of you have heard this before, but just pointing out that if you know these rules, all calculations can be done. Once I know the partition function, any observable connected to E can be computed. For example, if I want to compute expectation value of E, I look at this expression, I take a derivative with respect to beta. Then this E comes down. So if I take a derivative of del by del beta of log z, I get expectation value of E. Of course, in the previous one, so this takes the role of omega, the number of microstates. Now it is a partition function. So we need to addendum to rule 2. Just like we had entropy was k log omega, now we have some free energy which is E minus Ts. That free energy is linked to the partition function through this formula. This also can derive, but we can take it as given. So if I tell you that the connection to thermodynamics is F is minus Kt log Z, but F is E minus Ts, so if you do dF, you get TdS, that is dE minus PdV plus mu dN minus TdS minus SdT. So dF becomes minus SdT minus PdV plus mu dN. With this much information, now you can compute everything. Okay. So as an example, we will do it. Okay, this is just summary. You calculate Z, you calculate F is minus Kt log Z, you use the thermodynamic equation. If I do derivative del F by del T, I get entropy, del F by del V, I get pressure, del F by del N, I get chemical potential. Okay, so this is a calculation which is exactly same as the microcanonical calculation, but for a different constraints that you put on the system. So let us do one trial, one simple calculation, which is again a standard calculation, ideal gas. So given an ideal gas, you want to compute partition function in d dimension. There are n momentums, n positions. You integrate over all of them, e to the power minus beta times E, given whatever the configuration and momentum is. But for the ideal gas, E does not depend on x, it depends only on momentum, summation pi square by 2m. So I plug it back inside here. All the integrals become independent. So there are, P1 has d into n integrals. Each integral gives you a Gaussian integral root of 2 pi m kt, and this is the answer. Okay, I just go through fast because I feel most of you have seen this. So this is a partition function calculation. And once I have that partition function, I can say free energy is minus kT. I follow the same procedure, minus kT log this one. But I know the equation dF is minus STT minus PdV plus mu dN. If I do del F by del V, I get minus P. Why? There's only one term here, minus kT n by V, which is minus P. I get my ideal gas equation. So a very simple calculation. So the same problem, if you do the microcanonical ensemble or the canonical ensemble, you got the same answer back. Okay. So with these two rules, now we can generalize to any other ensemble, ensemble meaning what you keep under constraint, and other corresponding thermodynamic free energy. Okay. So let me run you through the next rule number 3. Suppose you kept now number of particles not fixed, but chemical potential fixed. So you are fixing T, V and mu. If you do the same argument, your probability of a microstate becomes e to the power minus beta E plus e to the power beta mu n. You can normalize it with a grand canonical partition function, which is the sum over all configurations, that means all over all E and all n. Then once I give you a grand canonical partition function, I have a rule addendum, which is some other free energy, E minus Ts minus mu n. Previously it was E minus Ts, this we can call grand potential, that is minus kT log L. And once I know that, I know how to compute dg, because dg is dE Tds minus Pdv plus mu dn minus Tds minus STT minus mu dn minus ndv, and you get this. So starting from the initial microcanonical rules, if I ask you that I'm going to relax one of the variables going to fluctuate, any of them, pressure, if I let volume fluctuate and keep pressure, you should be immediately able to find out the corresponding, the weight of a configuration and the potential. Okay, so there is nothing very particular, there is no need for a name, Gibbs potential, Helmholtz potential, all those names are not required. For every corresponding partition function, there is a corresponding thermodynamic potential, which you can figure out yourself without having to remember what corresponds to what, by just following these rules. Is it okay? Now, so quickly, so now let me do one calculation to show you that some of the calculations are much simpler. Now there are many questions that come. If I change ensemble, will the equation of state change? Sometimes calculations are simpler in different ensembles, but you have to ask whether when I do them in different ensembles, do I get the same answer back or not? So let us go back to the problem we did before. Okay. So what is the problem? You have a V lattice n particles. If two particles are on the same site, you have energy epsilon. But I want to do an ensemble where number of particles are fluctuating, number of energy is also fluctuating. So that partition function I called as L. So I have V sites. In each site, I could have 0 particles, 1 particle, 2 particles, right? 0 particle. So what is L? Remember, energy comes with weight e to the power minus beta epsilon, and number of particles come with weight e to the power beta mu, which I'll call as Z. So let me write an answer. Just by inspection, I can write L is equal to 1 plus Z square e to the power minus beta epsilon to the power V. So previously we had a lot of trouble counting. Now when I change ensemble, I am telling that I could have each site 0, 1 or 2. The next site is independent of the first site. The third site is independent of first and second site, and so on. So suppose I were to write, remove this V, for the first site, when 0 particles are present, I put a weight 1. When 1 particle is present, I put a weight Z. When 2 are there, I get a weight Z square. But there's an energy weight also, e to the power minus beta epsilon. Then I write something for the second site. So this is for first site. 1 plus Z square. So suppose I have just 2 sites. So this is second site. When I expand, first I get expansion 1, 1. That corresponds to empty, empty. Then I get 1 Z. That corresponds to empty 1 particle. 1 Z square e to minus beta. That corresponds to 1, 1, 2. Okay. So if I were to expand this, each term I can say Z times Z. 1 particle in 1 particle in the second site. So the counting becomes very trivial. The counting becomes by inspection, and my L becomes 1 plus Z plus Z square e to the minus beta epsilon. Is this argument clear? So, this is argument. Suppose argument is clear. Then I ask you a question where if I can have 3 particles per site and energy epsilon 2 if 2 particles, there are 3 particles in the third site. How will I modify this partition function? Plus Z cube e to the power minus beta epsilon 2. Okay, so the counting we took so much time to do last time has become just by inspection. But now we want to check whether if I start from this problem and now I want to find, given this partition function, I want to find pressure as a function of rho and T. And I want to ask, in the microcanonical calculation I did, does it match with this one? Okay. So I want to do this one. So first, how will I do? Okay, so remember your L was summation something omega summation overall configuration e to the power beta mu n e to the power minus beta e. This I wrote as z to the power n. So if I take del L by del Z times Z, I get summation n z to the power n. So if I were to divide by log L, I get divide by L, and this becomes expectation value of n. So to find expectation value of n, I have to do Z del by del Z of log L. And that is easy to do because I get V, logarithm of this is this particular quantity, V into Z plus 2Z square e to the power minus beta epsilon by 1. So that is my answer. So that gives me density. So that gives me rho is Z So we have found out rho in terms of this Z is sometimes called fugacity or activity. So sometimes I may use the word fugacity, activity. Does it have the correct limits? When z tends to 0, you look at this weight, z to the power n, the answer should be 0, meaning any particle, only for n equal to 0 there is a weight, so density should go to 0 and correctly rho goes to 0. When z goes to infinity, this term is important, this term is important, rho goes to 2. And that's the maximum density. As I increase my activity, it becomes maximal density. Okay, so we have the correct limit here. So that is density as a function of z, but I need to find out also what is pressure. We are interested in this quantity, pressure. So we go back to the L is minus kT g log z log L minus kT v log 1 plus z plus z square beta epsilon. Then you say that del g by del v is minus p, I think so. Then you get, which implies p by t is log 1 plus. So that's it. So we have found out pressure, we have found out temperature, we have found out pressure as a function of z, rho as a function of z, and what I want to plot is, if I plot pressure as a function of rho, do I get back my calculation I did in my microcanonical ensemble? So this, okay, is this okay? So I go back to my Mathematica. I go back to Mathematica. Now we don't want to mess up with what we had earlier. So this was called minus log S2. Okay. So let us now first, we want to eliminate Z. We want pressure as a function of density, Z we want to eliminate. So we can use this expression to find out Z as a function of rho. So solve rho minus z plus 2z square exponential minus epsilon So we are going to solve for z. That will be 1 plus z plus z square e to the minus epsilon equal to and we want to solve this for equation for z. And so again 2 roots came, but remember z is positive, so let us call this as w. Okay, I don't want to call this as w, I'll call this as w1 is this one, w2 is this one. So we have got 2 roots for z. Now I plot, let's keep epsilon equals 1, plot w1. That's a nice positive number. If I plotted w2, it becomes negative. So we are interested in w1. Okay, so we just on the basis of sign, we eliminate one of the roots from the 2 roots, and right answer we want is w1. And we want to clear. Okay. So what do you want to plot now? We want to plot pressure. So plot, and pressure was what? log of this one. And we want to define z is w1. So I think before that z is w1. And now we want to plot this. And you have got a pressure as a function of density. If I make epsilon, so now I want to plot this together with, so we have done this calculation. We have got pressure as a function of density. I want to compare this with the previous plot minus log S2. That will be, oops, log of 1 plus, epsilon equal to 1. Didn't match. Unfortunate. What is the error we made? Somewhere we made an error then. Epsilon equal to 1. So that is a nice exercise for you to try. Clearly, No. But let me just point out that unless I made some error somewhere, minus log S2 and log this. So I made an error. They should have matched.
Sir, I have a doubt. In the expectation of En, so like should we also divide by L, right?
We should divide by V.
I mean L.
When I do this N, I get a V here. So N by V I am calling as rho.
Yes, sir. No. Z by L, dou by dou Z of ln L, right?
Z del by del Z of log L.
The whole divided by L, right?
L is what? No, log L will take care of the 1 by L. Is 1 by L, this 1 by L del by del Z of L is del by del Z of log L. If I do del by del Z log L, I get 1 by L outside, then I get del L by del Z. It's the same thing. Okay. So I made some error which is very nice because you people can do it one more time yourself and check. Doing on the board, doing Mathematica in front of all of you is not did I do this? Z square equal to minus epsilon. Can you spot any error? W1 plot log of 1 plus Z square. This is my pressure. This is my pressure. I substitute for Z. So error must be in the other one. So we have, if we have done the calculation correctly, we have violated one of the rules that whichever cannot ensemble do the calculation in, you should get the answer same. But either we have done correctly and proved that result wrong, which is very unlikely. So you must do this. Doing a calculation by yourself makes you familiar with all the nitty-gritties that come in. I did quite randomly on the computer. So, and the answer is wrong. Which one? I don't even know which one I did correct. Did I do the canonical one correct? No, micro-canonical right, or did I do the grand canonical right? That also is not clear. Okay, so unfortunately I cannot fix it. So I will leave this as it is, and P is correct, rho is also correct. And did I solve it correctly? I must have solved. Okay, I think I did. Somebody has to tell me tomorrow that they could get it right, this calculation. It's a bit beyond the ideal gas calculation because it involves some energy also. So please try it if possible, if you have time. Now I will actually not do more than this. So So let me try to, so to do a StatMech problem, there are only a few rules you need to know. These are the rules you need to know. Then you have to do some complicated, you have to take some example of some system of interest, which cannot be solved like this. We have taken some very trivial examples to solve, to illustrate how to do the calculations. But when you do more and more interacting problems, for example, if I put a particular site 1, then site 2 cannot be occupied, or something like that, you can get more and more complicated behavior. So, but unfortunately, they are not most of the time solvable by hand, and the way to do them is by computer. And it's very good to know how you would tackle these problems on a computer. So my remaining, so let me just tell. So let me just take a little bit of time and motivation for. So we have been doing equilibrium StatMech up to now, no dynamics. You are only given an interaction, Hamiltonian. And the recipe for calculation is the canonical ensemble is, you have a configuration has energy E, then the probability of the configuration is e to the power minus beta E by the partition function, which is what we discussed. So now the aim is, I want to do this on a computer, but I cannot generate all configurations on the computer. So I want to generate independent, I want to generate configuration C1, C2, C3, C4 and so on. But each C1, C2, C3 don't come with the same weight. They have different probabilities e to the minus beta EC. So I should be able to do the programming in such a manner that configuration C1 comes with probability e to the minus beta EC1, C2 comes with the probability e to the minus beta EC2 and so on. If I could generate configurations of that by like that, then all I have to do is I take configuration C1, I measure energy, for example, C2 energy C1, I average over all of them, and that average gives you the final answer, the macroscopic variable. This is what I would like to do. Is this clear? So, with this slide, so now this is true, not even for a problem in equilibrium, for a problem not in equilibrium also this is true. So now if I want to generate configuration C1, C2, C3, C4 and so on, I have to now also talk about dynamics. What dynamics should I give to a statistical system so that the configurations are generated with the correct statistical weight? So I have to choose some dynamics, and we will choose something called Markovian dynamics, which means that the new configuration only depends on the configuration at this time, current time. So if I know the current time, I will be able to tell you probabilistically what's the next configuration going to be. So once I choose the dynamics, I have to ask, the questions come, how can we define the dynamics so that we get the correct equilibrium weight? How do you simulate on a computer? And what dynamics will generate equilibrium weights? So these, if I could answer these three questions, then I have to just put them on a computer and you can do complicated problems as and when they come. Okay, so I will stop at this point and we'll do we'll do the remaining tomorrow as much as possible. Any questions? But I hope one of you at least tries this and finds out what mistake did we make in that calculation.